Okay, so let's talk about the assumptions that you might have with this equation. Assumptions. So first of all, problems are going to tell you the same thing they did before. What if they had it's adiabatic? Okay, adiabatic means that the heat transfer rate is equal to 0. Okay, now sometimes they're not going to specifically say adiabatic. Sometimes we're going to have to assume adiabatic or model it as adiabatic, and I think we're going to start getting the practice of when that happens. All right, and I'm going to give you some hints about when that's going to happen here a little bit later. All right, basically we're saying in many situations the heat transfer rate for the control volume is so small that it's negligible. Okay, we might have that situation. Why does that have that situation? Because it's insulated. We might have an insulated situation. We might have a small surface area or outer surface area. No place for the heat to be transferred out of. Can't do that. Well, how is it going to be transferred out of? Through conduction, convection, or radiation, because that's that Q dot that's happening here. You could have maybe that your delta T is small. Flow is going really fast through an object, something that you're dealing with, a pump, a turbine, or some sort, and you're saying, man, the delta T there is very small, and so where does the heat have to go? The heat has to be... can't be leaving the system because there's not enough delta T for that to lose any heat. Okay, all these things could be what you were to see for Q is equal to 0. Q dot is equal to 0. Okay, when are you going to say that W dot control volume is equal to 0? Where are you going to say that if there's no shafts? If there's no shaft that you have that's coming in or out of that system, not going to be any power. Can't power it by externally or can't create power from that. You're going to have no displacement. And it's probably a good thing not to have displacement for these control volumes. If you look at a control volume and it starts to displace, it starts to get bigger, if you're around a pump and that pump starts to increase its volume, run. It shouldn't be doing that. That's a big problem. There shouldn't be any boundary work happening because of your control volumes. Okay? You have to look for electrical work, of course, to see if that electrical power, I should say that electrical power here, that we're not powering it by plugging it in, or something like that's happening. Those are things that we're going to see there quite often. Of course, if kinetic energy and potential energy effects are often negligible. We'll talk to you about the situations where they're not. We'll go through those step by step. But usually the kinetic energy of the object of the flow coming in is very similar to the kinetic energy of the flow coming out. Same thing with potential energy. So this will be our most common assumption, our model that we will make. And the last thing we'll say is steady state. Steady state is going to be our typical assumption, and everything we're going to consider is going to be steady state. And that's going to say the change in energy of our control volume with respect to time is equal to 0. Now, realistically, things are not steady state. Okay, if I look at steady state, what's going to happen here is, let's just talk about a pump. I think most of you are familiar with a pump. Let's just say there was a bunch of water that's located maybe in a pond or in a bucket or in a pool. Let's say do a pool. We want to pump the water out of that pool. Okay, when we would put a suction line and we would have a flow line coming out of there, what we would notice is that as we started that pump on, this is our time axis and this is basically our energy axis here, we would notice that we would start up and we would kind of go like this until we got this pump running. It's that starting up. That's my pump sound today. I guess that's my pump sound today. We'll go with it. That's my. And then at a certain point in time, it's going to now start to become, now it's running, operating steadily, and that's going to go out like this. Now, no, look what's going to happen. It's going to go up, maybe down, maybe a little bit, but it's going to come down like this, maybe a little bit. This is what steady state actually looks like. Maybe it goes like this. This is what we're going to model as steady state. It's not really steady. It's not perfectly boom. It's not changing. It is approximating itself as being steady. And that's why we're going to say that the change in internal energy of our control volume is equal to 0. Now, let me just say right now, everything that you're going to be talking about right now for this chapter is going to be steady state. We're going to assume or model a steady state. Sometimes the problem statement is going to definitely say a steady process, and sometimes it's not. But right now, assume everything is steady state until I tell you otherwise, and then we'll look at what we do in transient systems or what we do in situations when we're back to this situation. Okay? That's what I want you to look at. Okay? Now, if you see a control volume at steady state, what you know is, so at steady state, the mass flow rate in, or sum of the mass flow rates in, is equal to the sum of the mass flow rates out. Okay? Because what happened here, the change in mass of the control volume with respect to time is equal to 0. The mass did not change in that control volume over time. The other thing we can say at steady state, the change in energy of that control volume with respect to time does not go, it goes to 0. And so the energy coming in is equal to the energy going out. Sometime we'll do that as Q dot plus the summation, the heat transfer plus m dot n times the enthalpy n plus the kinetic energy n plus the potential energy n is equal to the summation of the mass, or the power going out, plus the summation the mass flow rate exiting times the enthalpy exiting, the kinetic energy exiting, and the potential energy exiting. Okay, that's what could happen. I don't really write the equation this way so much because I don't like splitting it up. I like to have the transfers on one side and everything works on that way, but this is another way to write the equation. Whatever works for you, I'll accept that. Okay, but you have to know the steady state thing is going to be a very important situation that we're going to be dealing with. All right, often we're going to have one inlet and one exit. That's a special case. So special case, if we have it's steady state, and then we have one inlet, one exit, what your equation is going to be is 0 is going to be equal to the summation of the heat transfer of the control volume minus the summation of the power of the control volume plus m dot times h in minus h exiting plus v entering squared minus v exiting squared over 2 plus g z entering minus z exiting. Okay? Why do we do it this way? Because the mass flow rate in has to equal the mass flow rate out if it's one inlet, one exit. So m dot in is equal to m dot out. We can pull that out of the equation and we can work with it here. Now I want you to recognize here these things cause problems because of units. Okay? The units of enthalpy are in kilojoules per kilogram. The units of kinetic energy, we're going to have to convert ourselves to kilojoules per kilogram. You just can't just plug and chug. That can't happen. So whenever you see a problem with kinetic or potential energy effects, you're going to have to work on making sure your units work out. Sometimes the problem statement will ask you, what was the heat transfer per unit mass? Okay, they'll say, what is the rate of heat transfer or the rate of work per unit mass? Okay, so what we're going to do there is we're going to divide through and say that Q dot control volume over m dot, and that's going to be in units of if this was going to be in kilowatts per kilograms per second. Remember that kilowatts is a kilojoule per second, so this might give us in kilojoules per kilogram. They might say, what is the heat transfer rate per unit mass? And they say in units of kilojoules per kilogram. See how the units all work out there. A kilowatt is a kilojoules per second. A mass flow rate is a kilogram per second. The seconds cancel and you get kilojoules per kilogram. Same thing works in the English engineering units. Okay? They'll do the same thing for W dot over mass flow rate. They'll say in kilojoules per kilogram. Sometimes what we'll do in some books, and it's not this book, but some books, or you'll see it around, they'll write this as lowercase qCV. They'll write this as lowercase work CV, because remember, whenever we take something and divide it by mass, we have the specific work, or the specific heat transfer. So they might call this the specific work, or the specific heat transfer. These are words that are being used. Okay, these are words that are being used. So right there, this is, we'll manipulate and use this equation over and over and over again. But what I'm going to show you in the next series of videos is we're going to look at specified control volumes that we're going to be talking about throughout this class. We're going to talk about nozzles and diffusers. We're going to talk about turbines and compressors and pumps and heat exchangers and throttles and flash chambers and those kind of things. And we're going to say these are things that you're going to see. These are characters in our story, and show you how you're going to deal with these characters. But really, everything that I need to do is I've already provided you with that right here. And we'll see that in our next videos.